We're going to start off our treatment of rotation in quantum mechanics by talking about how rotation is treated in classical mechanics. So, in classical mechanics, rotation is, we have angular momentum, L, and it's given as r cross p, where r is the vector from the, right here, oops, r is the vector from the origin to the object. P is the linear momentum of the object at that given time. So classically, that would be just m times the velocity vector. And then the angular momentum is the cross product, the vector quantity is the cross product. We take the right-hand rule, rotate, and that will give us the direction of our angular momentum vector. So in classical mechanics, we have angular momentum, which is the distance, actually the vectoral quantity, distance the object is from the origin, from the center of rotation. We have the linear momentum, P, classically is equal to mass times velocity. We've already done. And I'm going to stop again here. So, the kinetic energy is going to be equal to 1/2 I omega squared. I is the moment of inertia. It's a generalized mass. Omega is angular velocity, so d phi dt, where phi is the rotational angle. And so much like straight line motion, the kinetic energy, the straight line motion, the kinetic energy is a mass times the velocity. And for rotation, then, the kinetic energy is, again, a generalized mass, the moment of inertia, times a angular velocity squared. We can also put this in another way, that we have it's equal to the kinetic energy is equal to the angular momentum squared over 2I. If we think about this, for straight line motion, it's equal to p squared over 2m. So again, we have an analogy that between energy for rotational motion and energy for straight line motion. Now, what about if I have, so I think okay. What if I have a more complicated object? And I put together here a structure, okay, this is the benzene molecule, of course, and put together a coordinate system. So our C3 axis is right here. And the angular momentum about the z-axis now is just going to be the sum of the angular momenta of all of the n atoms. So if I'm rotating about some axis, the angular momentum about that rotation is the sum of the momenta of all of those n atoms. The kinetic energy is going to be the moment of inertia. Again, I'm calling this Iz because we're rotating around the z-axis. So Iz, 1/2 Iz, times the frequency rotation squared. Again, this is going to be d phi dt. Now, for a generalized object, we're going to start with a generalized object and go back to simpler ones. There are rotations around other axes. And in general, the moment of inertia is a 3×3 tensor. Lest a tensor scare you, really it's just a matrix. So, but it's a physical quantity that has the form of a matrix. The elements of this tensor, the diagonal elements, are just going to be the mass of each object, the sum over all objects, the mass of each object times x squared plus y squared. What is that? That's just the distance away from the center of rotation for each object, because that's now in the xy plane and it's rotating on the z. Off diagonal elements are going to be cross products between positions in different, so in this case, Ixy is going to be equal to mi xi yi for that particular object. And similarly, we'll have an Ixx, an Ixy, Ixz, and this will form the elements of a 3x3 matrix. We can simplify this greatly, and this is one of the first things one would do if you're doing this classically, is you would always choose you can choose any set of axes, rotate your coordinate system, find some set of axes such that the off-diagonal elements are equal to 0. Then it becomes 3 separate rotations with 3 separate moments of inertia, and they're not coupled together. Our convention for this is going to be that the moment of inertia for axis A is less than that of B, is less than that of C. Okay. We're going to start off with a diatomic molecule, and because that's going to be one of our simplest cases. The molecule is going to rotate around the center of mass. The center of mass along any coordinate is just going to be equal to the sum of all the masses times the coordinate divided by the mass of that. So in other words, in this case, it's going to be equal to, we'll just take our coordinate as being r. In this case, it's going to be m1 r1 plus m2 r2 divided by m1 plus m2. So we can, which is stated here, if we set our center of mass to the origin, then the center of mass must be equal to 0. And we can do a little manipulation. We can find out that R1 is equal to M2 over M, the total mass, times R. R2, the length of the, for M2, is M1 over M1 plus M2R. It's a nice little proportionality. And we can show that then the total moment of inertia is going to be equal to M1 M2 over M1 plus M2 R squared. And this, of course, is just the reduced mass for if you've been looking ahead. Okay, the angular momentum, again, is going to be equal to the moment of inertia times, now I've completely expressed omega as a vector, and the moment of inertia is equal to mu r squared omega. The kinetic energy is equal to I omega squared over 2, or L squared over 2I. When we get to quantum mechanics, this is going to be the thing that is going to be useful, because it turns out that L squared is a operator that we can determine values for.